This video is part of CAE Associates Ansys e-learning series. CAE Associates is an engineering consulting firm in Middlebury, Connecticut, specializing in finite element analysis and computational fluid dynamics. We have been an Ansys channel partner since 1985 and have developed our Ansys e-learning series to help you maximize your software investment. Please visit our website, which includes an extensive resource library with over 250 items and counting in an easily searchable area. We also invite you to visit our Engineering Advantage blog, where we share insights from our many years of performing engineering analysis. CAE Associates also offers an extensive schedule of Ansys courses taught at our Middlebury office. If you need help deciding on the best courses to take for your application, visit our CAE University page. The complete library of e-learning recordings is available for viewing in our resource library and also on our YouTube channel at youtube.com/CAEAI.
And the topics we're going to cover today are an introduction to the Workbench LS-Dyna product, and I'll discuss what it is and some of the features that are available within the Workbench Dyna product. And then I'll go through a fairly straightforward demonstration of a copper cylinder impacting a plate, both a rigid and a flexible plate. Okay, moving on. What is Workbench Dyna? Workbench Dyna is a new user environment for pre-processing, solving, and post-processing LS-Dyna models. It combines the power of the Dyna solver with the ease of use of the Ansys Workbench environment. So if you're familiar with the Ansys Workbench, and particularly the mechanical interface and the design modeler interface, this should be fairly straightforward to pick up because the interface is the same. There are just some additional menus that are available for setting up the Dyna model. If you're not familiar with Dyna, LS-Dyna is the leading commercial explicit dynamics solver. It's very robust, it's fast, and it's used for solving high-energy transient dynamic events. The applications typically include impact analysis, drop test analysis for commercial electronics, for cell phones, for computers, laptops, and so forth, crash dynamics analysis, manufacturing problems, buckling, and so forth. The Workbench Dyna is the result of a collaborative effort between Livermore Software Technology Corporation, they are the developers of LS-Dyna, and Ansys Incorporated. Workbench Workbench LS-Dyna works with version 14.5, not with any of the prior versions of Workbench. And at the bottom, we have an image of an analysis that was done with LS-Dyna, obviously very complex, of a full vehicle crash. Moving on, the product requires an Ansys LS-Dyna license. The utility itself is installed separately from the standard Ansys install, and it's available from the Ansys customer, or will be available from the Ansys customer portal extension library at no extra cost. It's not up there yet. It hasn't been officially released, but it should be released towards the end of this month. The interface was created using the newly released Ansys Customization Toolkit. You may have heard of this. This is the ACT utility. This utility enables customization of Ansys Workbench interfaces. So you can set up your own menus within Ansys Mechanical or other Workbench environments. Customers can license ACT. If you want to do any customization yourself, you could license ACT customization for, say, static analysis, or you can customize it to create your own menus for LS-Dyna in case there are some capabilities that are not included within this tool. Parallel processing is fully enabled, so you can use, assuming you have the license for it, you can use the parallel capabilities. Also, if you're an advanced Dyna user, what you can do is you can write out the .k file directly, and then you can add additional commands to the keyword input file, which is the Dyna formatted input file. And at the bottom, you can see another example of a Dyna analysis, which is a can crush type of analysis. So it's very, the Dyna solver is very robust for this type of application where you have significant contact, very severe deformations, and high strains and plasticity. As I mentioned before, it uses the Workbench mechanical interface. So if you are familiar with that interface, it won't be too much of a stretch to learn the additional menus that are required to set up the Dyna model. Some additional features. There is and has been a Workbench LSDyna export tool that's been available for a couple of prior revisions of Workbench. All of those features are still available. Now, the limitation of that feature was that it didn't have an extensive pre-processing library, and in addition, you couldn't do any post-processing with that tool. You had to write out the Dyna input deck, run it separately, and then post-process using the LS-Prep post-processor, not Workbench. So one of probably the biggest advantages of this new Workbench LSDyna tool is that that you can post-process within Workbench. All the CAD import capabilities are still available. All of those tools that you have within Workbench are still there. Geometry cleanup tools are there. You can parameterize the geometry, loads, properties, and results, so you can make it a fully parametric model. It has access to most of the contact features that are available within LSDyna, including bonded or tied contact, frictional contact, eroding contact, single surface contacts. You can assign rigid bodies and rigid body loads. You can apply pressures and forces, also initial velocities, both translational and rotational velocities. You can assign and set up longitudinal and torsional springs and dampers. You can apply symmetry constraints, point masses, rigid body or rigid joints between parts. And it also supports most of the Dyna solid and shell formulations. There are many, many different shell formulations, for example, that you can now assign within the Workbench environment. And as I mentioned before, it has a comprehensive set of post-processing tools. You don't need to learn LS-Prep Post anymore. All right, let me ask you a question here. I'm going to set up a poll question and ask you whether or not what level of experience you have with LSDyna. Have you ever used it? Have you seen it used? Do you have some experience with it, or do you use it frequently? So let me open up this. 38% of you have never used it. 28% have seen it used. And then a smaller percentage have some experience with it. So the majority of you have not, don't have much experience with LSDyna. Okay. Let me move on here. Let me go on to the demonstration problem here. And what I have is a copper cylinder. It's 2 inches in diameter and 2 inches long, and it's impacting a steel plate at 400 miles per hour. So it's moving pretty fast. This is essentially a Taylor bar impact test, which is used for determining the yield strength of metals at impact velocities. And what I'm going to do is I'm going to solve this first with a rigid plate, and then I'm going to change it to a flexible plate, and we'll see what happens. And you'll see what I have here is I have an engineering data component system for setting up material properties that's linked in with a Workbench LSDyna analysis system. Okay, the geometry is already set up, and there's some parameters that I've defined for some of the dimensions of the copper cylinder and also for the thickness of the steel plate. Let me open up mechanical. This is what the geometry looks like. Very simple. And what I want to do is when I first import the geometry, I want to define this plate as a rigid body. So I'll click on the surface body, and you'll see down under the details pane, it's set to flexible. And I'm going to switch that to rigid. And having rigid bodies is very useful for speeding up an analysis. So in parts where you don't need to have a stress solution or a strain solution, you can define those as rigid bodies, and it'll speed up the solution substantially. Okay, the thickness is parameterized, so I can easily change that in the parameter manager. What I'm going to do now is I want to go back to the engineering data page, and I want to set up my copper material and assign that to the cylinder. So right now I just have structural steel defined. I'm going to click on this library icon and access the general nonlinear material library. And in that library, I have a copper alloy, NL, for nonlinear. I'll just click plus here. That'll add that to my engineering data library and make that available for my model. So now when I click on the contents of engineering data, that table includes the copper alloy. If I highlight the copper alloy and look down in the table of individual properties, you'll see that my yield strength is about 40,600 psi. I want to soften that up a little bit so I can see some significant plastic deformation when it impacts. So I changed that to 30,000 psi. I'm going to return to the project page. Actually, I'll go back to the mechanical interface. I'll select Model, right-click, and refresh material. So this is the same procedure you would use for static analysis. Under solid, this cylindrical body, I want to change the assignment of the material to, let's see, I think I have to refresh the material list again. Okay, I don't see it there. Let me go back and make sure I have this set up. Okay, I do have copper alloy defined. So let me go back here, refresh the material, right-click on structural steel, and I still don't see it. So what I'm going to do, I'm going to go back here, and under Model, I'm just going to right-click and refresh. Okay, now I have copper alloy NL available. So that's properly assigned to my cylinder. Let's check my contact definitions. Under connections, I have this item called body interactions. If I look there, it just says body interactions. Now that's if you're familiar with Dyna, that's a single surface contact type. So that checks for contact between the external surfaces of all bodies, or I should say all parts in my model. And I can change that to frictional contact or to bonded contact if I want to. I'll change it to frictional and just give it a very small friction coefficient. And I can use dynamic friction as well as static friction. Let me select mesh. I don't have a mesh assigned here yet. Now, if I click on mesh, you notice the physics preference is set to explicit. And that's important because it has to use lower order element types without the mid-side nodes for LSDyna. So by using a Workbench LSDyna analysis type, it's going to automatically mesh these with 8-noded bricks or 4-noded TED elements. Now, if I right-click on this and choose Generate Mesh, it's just going to create a default mesh for me. And what you'll see is, if we look at the cylinder, I've got some relatively small elements in the center of that cylinder. And I don't like that because small elements tend to drive your time step down in explicit analysis. So we prefer to have a more uniform distribution of elements with fairly uniform element sizes. So to achieve that, what I'm going to do is right-click on Mesh, insert a method, assign that method to my cylinder, and I'm going to change that method type to multi-zone. And that's a hex mesher. And when I regenerate the mesh, I should get a more uniform distribution of elements, which I do. So fewer elements, and the element sizes are more uniform. Okay, moving on to the Workbench LS-Dyna analysis. I want to assign my initial velocity to the cylinder. So I click on the Initial Conditions folder. I choose Insert Velocity. I select the cylinder. I'm going to assign the velocity of 7,000 inches per second, which is approximately 400 miles per hour. The direction, I can assign the direction by picking a face. That direction is normal to the face. It's not in the correct direction yet. It should be in the negative Z direction. So I switch the direction, and the arrow's pointing now towards the plate. Now when I select Analysis System, this is where I can define the total transient time. So the end time of my analysis is going to be 3 milliseconds. So I want to put 003 in here. I want to change my unit system to the British inch-pound-second unit system. So that's used in the solver. And I could change the number of CPUs to use in my analysis. So if I have a license for parallel processing, I can increase the number of CPUs. I want to change the hourglass type. The default hourglass type typically is not the best choice. So what I can do is switch this down to any of the available Dyna hourglass control types, and I'll choose the viscous exact volume integration or exact volume Flanagan-Belichko type. And I can change the hourglass coefficient if I wanted to, but I'll take the default here. Under output controls, I can specify how many output points to write to the results file. If I click on Calculate Results, it's set to program control. I can change it to equally spaced points. And right now it's set to 20. Now 20 isn't really a lot of points. It won't give you a very good definition of the results. So I typically want to increase that number, and I'll choose 80. That'll give me 80 result sets in my results files. Okay. Now, I have my initial velocity defined. I have my analysis settings defined. What I want to do is I want to fully constrain this rigid plate. So I'll right-click on Workbench LS-Dyna, and I'll insert a rigid body constraint. I'm going to pick the plate, apply it to the plate, and by default, all of the translational and rotational directions are fixed. And I could free those up if I wanted to. Now, the other thing I want to do is I want to make this a little more interesting. And to do that, I'm going to apply an impulse load to the very top of this cylinder in the X direction, so in the transverse direction. That's going to cause this cylinder to rotate a little bit before it impacts. So it's going to tilt as it's traveling towards the plate. So to do that, I right-click, Insert, Force. I'm going to apply that force to the top face of the cylinder. I'm going to change the define by to components because I want to define this in the global X direction. There's a table down at the bottom that I can modify. And what I'm going to do is I'm going to set up an impulse load. And that impulse load is going to go from 0 to 10,000 pounds and back to 0 in 0.0001 seconds. So you'll see the graph of that impulse load here on at the bottom. It's just a triangular impulse load. And now we're ready to solve the analysis. What I want to do is insert some results. So I'll insert deformation, total deformation. I'm also going to insert a user-defined result, and this is required for plastic strains. If you want to look at plastic strains, at the moment, the way this is set up is you have to insert a user-defined result, and the expression is EPS. I also want to track energy data, and to do that, I go up to the menu near the top, and I can extract information from a variety of ASCII files that get written from the Dyna analysis. And one of the most common ones to look at is this global data result file. So if I click global data, what I can do is I can graph. This allows me to graph energy data from the analysis. So I could pick items like global kinetic energy, global internal energy, global hourglass energy. Let me choose those three and click Apply. Now I'm going to solve this. So I right-click, Solve. And this solves pretty quickly. So it's 3 milliseconds of transient time. And it automatically calculates the time steps for you based on the wave speed, the elastic wave speed through each of the parts. So let's take a look at these results. Now, if I look at the plastic strain result, that's about the most interesting result we have, I can animate this over time. So you can see that the cylinder comes in, impacts the rigid plate, bounces off, and we get a significant amount of plastic deformation. If we look at the contour bar, we have about 61% peak plastic strain in here. And I can dynamically rotate this while it's animating. The other thing we can look at, let me stop the animation. I can graph the energy data that I requested. And so this is a graph of kinetic energy in gray. And then the green line is internal energy. So once it impacts, the vast majority of the energy gets transferred to internal strain energy in the cylinder, in the copper cylinder. And then I have hourglass energy as well, which is something you typically want to track to make sure that you don't get too much hourglassing in the elements. And that is that energy we see there is pretty small. Okay, so that's our first case. What I want to do next is I want to change this plate to a flexible plate. So I switch this, click on the surface body, and I'm going to change the stiffness behavior down here from rigid to flexible. You'll notice down here that under Workbench LS-Dyna, the rigid body constraint item has a question mark next to it. That's because I don't have any more rigid bodies in my model. So I want to suppress that, and I want to constrain the right side, the right edge of this plate. So right-click, Insert, Fix Support. I'll change to Edge Select. I'll pick that right edge, click Apply. Now that edge is fully constrained. The other thing I want to do is I want to track the reaction forces. So now that I have a fixed constraint here, I can click on ASCII Output, Reaction Forces, and that's going to bring up a reaction force item under solution, and I can select that fixed support boundary condition, and it will graph the reaction forces at that constraint location. So let me solve this again. And again, this will solve quite quickly. It's extracting the results from the results files. And I have now when I look at the plot of plastic strain, I can't see my cylinder anymore. That's because it's bounced off to the left. So let's take a look at the animation and see what's happening here. Let me move this up a little bit. So you can see that there's quite a bit of flexibility in the plate. It's oscillating quite a lot. It bounces, and it actually bounces back and hits the cylinder a second time and creates a secondary dent in that cylinder. The one thing I forgot to mention is if you look at this from the side, trying to slow this down a little bit. Let me slow that down. There we go. You can see as the cylinder comes in, it starts to rotate about the global y-axis, and that's because we have that transverse impulse load. Okay. One more thing that I want to do here. Go back to the project page, and if you look under the parameter manager, I have a couple of design points set up. The one that I've been solving so far is for the case where we have a 2-inch diameter cylinder and a 2-inch long cylinder with a 0.2-inch thick plate. I have another design point, actually design point 1, which has a 3-inch long cylinder, 2-inch diameter cylinder, and a 0.25-inch plate. So what I can do is I can right-click on that design point, copy inputs to current, go back to the project page, and click Update Project. And that's going to update my geometry and resolve. So now if I click on Mechanical again, what you're going to see is you'll see the geometry will get updated. So the geometry's been updated now. It's going to remesh and resolve. So it's remeshed, and now it's solving again. So the parameter manager allows you to very rapidly see how changes in geometry or changes in inputs will change your results. Okay, I had a little problem here with, nope, it's fine. Okay, let me animate this. So now you can see this new geometry comes in, impacts the cylinder, and bounces off, creating a secondary dent, but in a different location. We can look at global data, and you'll see this is a very different looking kind of plot of the energy data. And we can look at the reaction forces. Actually, the reaction forces are listed down, a graph at the bottom of the page. And you can see they oscillate around significantly. Okay, so that's the end of my demonstration problem. What I'd like to do is open up a second poll, and I want to ask you if you think that this tool might be useful in your work. So let me open that up here. It's going to take me a second to bring that in. So I opened that poll, so I'll give you another minute to respond to that. Most everybody thought that it would be at least somewhat useful, if not very useful. Okay. All right, let me just list a few conclusions about this product. Workbench Dyna combines the functionality and ease of use of Workbench with the power of the Dyna solver. It's very easy to modify geometry, mesh loads, constraints, material properties, context settings, and analysis settings within the mechanical interface. It's also relatively easy to learn this tool if you're already familiar with Workbench and specifically Workbench Mechanical. You can also, one of the other big advantages, if you already have a model set up as a static structural analysis, you can always just simply copy that system over to a Workbench LS-Dyna system, and then you don't have to create a new mesh. You do have to assign new loads because the load application methods are different. The contacts are different as well, and the analysis settings are different. But certainly the mesh and the geometry would come over. Things like symmetry conditions would also come over to the Workbench Dyna analysis. Also, I do want to reiterate that you can now post-process with this tool within a Workbench environment, so you don't have to learn another post-processor. All right, thank you very much. I am going to try and answer some of your questions now. Okay.